Hi, this is Mrs. Villette, and in this video I'm going to be explaining some notes that are already filled out. So these are the section 4.2 notes. If you haven't already copied down the notes, then you should pause after I reveal each line and actually write down the notes. I'm just going to try to hit the important features. So in example 3, we're trying to find the equation for the function pictured. We're going to use the y-intercept to determine a stretch factor, if any, and then evaluate the function for very large values, both positive and negative, to determine the horizontal asymptote. So let's start with the information that we do have. We know that there are vertical asymptotes, and it looks like they're at x equals -2 and x equals 2. We have talked about the connection between vertical asymptotes. They are the zeros of the denominator. So that means there should be factors of x minus 2 and x plus 2 in the denominator. Next, I can see I have x-intercepts at -1 and +1. Those should be factors of the numerator. So that means there are going to be x minus 1 and x plus 1 in the numerator. The next thing we need to do is find the stretch factor. So we're going to put all of that stuff together. We have the x minus 1, x plus 1 in the numerator, x minus 2, x plus 2 in the denominator. And I'm going to throw a stretch factor out in front, and then I'm going to plug in this y-intercept, which is at 0, 1, to try to see if I can figure out the stretch factor. And it looks like the stretch factor is 4. Of course, plugging 0 in for x just makes this -1 times 1, which is -1. And then -2 times -2, which is -4. So I have -1 over -4, which is 1/4. And that means that your A is 4. So our conclusion then is that our function is 4 times x minus 1, x plus 1 over x minus 2, x plus 2. Or you could simplify and multiply out those difference of squares. Now the last part that I didn't do when I was filling out these notes was I forgot to figure out what the horizontal asymptote is. So let's go ahead and do that part. One way that we can figure out the horizontal asymptote is we can plug in a really large value of x. And it doesn't have to be particularly large, so let's just try f of 100. So I'm going to have 4 times 99 times 101 over 98 times 102. It probably would have actually been easier to evaluate this in the standard form, because then I would have just had 4 times 10,000 minus 4 all over 10,000 subtract 1. So 40,000 subtract 4. And then 10,000 minus 1, 9,999. Now you can see that that's pretty darn close to 40,000 divided by 10,000. It's pretty close to 4. It's a little bit less than 4. What does that mean? That means that with this particular function, it's going to be a little bit bigger than 4. As I go out really far, remember the definition of a horizontal asymptote is you go way, way far out, so x gets very large. The y values are approaching 4. Now you might wonder, is it a coincidence that my stretch factor was 4 and my horizontal asymptote is 4? And the answer is that no, it is not a coincidence. In the case where the numerator and denominator have the same degree as each other, so in this case they were both squareds, x squared and x squared, whatever the ratio of the leading coefficients is, so 4 over 1, that will be the value of the horizontal asymptote. Let's take a look at another one. You were supposed to do this one on your own, but we can go ahead and go over it together. So same idea, except this one does not have a horizontal asymptote. So we're going to start with the x-intercept. So the x-intercept is at 4, which means I'm going to put an x minus 4 in the denominator. There's an x-intercept at 2, so I'm going to put an x minus 2, and I'm going to go ahead and square it in the numerator because of this bounce. Then I solve for my stretch factor. So my stretch factor I'm just going to call a, and then I'm going to plug in this point 0, 1. So I'm plugging 1 in for y, 0 in for the x, and I get a equals -1. So here's my function, zeros or x-intercepts in the top, vertical asymptotes in the bottom. I checked it in Desmos, and everything looks good. In part C, it asks you to evaluate for large values of x to see what the horizontal asymptote is. So I started plugging values of x like 12, 102, 1002 in. And the reason I chose those is because those numbers, when I subtracted 2 from them, would be nice numbers. And it turns out that I was getting numbers like negative 12.5, negative 102, negative 1004. So as I was putting in large values of x, I was not settling on a single value of y. So what this looks like to me is what's called an oblique asymptote or a slant asymptote. And it looks like whatever the x value is, the function value is pretty close to the opposite of that. And in fact, if you go up here and you draw the line y equals the opposite of x, that looks like a pretty good approximation of where that slant asymptote is. So how do you know? Do I have a horizontal asymptote, or do I have a slant asymptote, or do I have nothing? So let's take a look at the next page. So there are 3 cases that can happen. As a reminder, the horizontal asymptote is a horizontal line that the function approaches as x goes to infinity or as x goes to negative infinity. There are only 3 possible cases for what can happen. The first case is there is a horizontal asymptote and it's 0. This is going to happen when the denominator degree is bigger than the numerator degree. So for example, if we had x squared as the highest in the numerator and x to the 4th in the denominator. What's going to happen here is as x goes to infinity, the top goes to infinity, the bottom also goes to infinity, but if we want to think about sizes of infinity, it's like a small infinity over a giant infinity. And that bottom goes to infinity so much faster than it pulls this whole ratio down to 0. Now the next case to happen is that there's a horizontal asymptote y equals b, where b is some non-zero constant. This will happen, as we saw in example 3, when the numerator and denominator have the same degree. So if I had 5x to the 4th over 3x to the 4th, 5/3 would be my horizontal asymptote. And the third case is there is no horizontal asymptote. It could be oblique or something else entirely. And this happens when the numerator degree is bigger than the denominator degree. So like you had an x to the 7th over an x to the 6th, or an x to the 8th over an x to the 4th. And this is kind of the reverse idea, where the infinity on top is much bigger than the infinity on bottom, and so it pulls this whole ratio up toward infinity. So in this next one, we've got some functions, and you are going to go do a Desmos activity to get this table of values. So the Desmos link should be on Moodle. What I want you to notice is that in all of these cases, we are letting the x values get progressively larger by a factor of 10. And in both cases, the numerator and the denominator should be going to infinity. But what we're concerned with is what happens to that ratio. So what happens to the numerator over the denominator as they both jointly go to infinity. So go ahead and do the activity, pause the video, and then come back and we'll talk about the results. Okay, so if you've done the activity now, you've noticed that in this first example, even at 100, the ratios, when rounded to 2 decimal places, ended up being 1.5. I think this last one I copied wrong. It should also be 1.5. And if you carefully notice, that is exactly what the ratio of the leading terms are. 3x over 2x reduces down to 3/2 or 1.5. In the next example, the numerator is a quadratic and the denominator is linear. The numerator grows much faster than the denominator, so as I'm plugging in bigger and bigger values of x, this ratio just keeps going up and up and up. It's not settling on a single number. In fact, each time it's going 1.5 times 10 to the 6th, and then 1.5 times 10 to the 7th, it's going higher and higher. So this one has no horizontal asymptote. So no HA, versus this one, the HA was 3/2. And then our last one, we can see the denominator grows faster than the numerator. So we start off with 0.32, then 0.03, then 0.003, and each time I increase my x, the number of leading zeros I have increases by 1. Remember, this is scientific notation, so 3 times 10 to the negative 7th is a very small number. So this one does have a horizontal asymptote, but it's y equals 0. The denominator grows faster, and it pulls that whole ratio down to 0. So our conclusion here is there are 3 cases. If the numerator and denominator are equal degree, the horizontal asymptote is the ratio of the leading coefficients. If the degree of the numerator is greater than the denominator, there is no horizontal asymptote. If the degree is 1 more than the denominator, so like x cubed over x squared, there will be what's called an oblique asymptote. And when the degree of the denominator is greater than the numerator, the horizontal asymptote will be y equals 0. I want you to just think about the relative sizes of the infinities in these cases. So let's look at some examples. Notice in the last example, part C, I've changed this to an x to the 6th. What we want to do for finding the horizontal asymptote, if they exist, is we want to look at the leading terms. So we're looking in the numerator for the highest exponent, negative 5x to the 4th, and in the denominator for the highest, and then we're just comparing those. So negative 5x to the 4th over 4x cubed, if you cancel, you would get negative 5/4 x. That actually means there's an oblique asymptote, and its slope will be negative 5/4. Notice the numerator has a higher degree than the denominator, so it grows faster. In part B, we have both leading coefficients are written right at the front, and we can just examine their ratio is 3/4. That's your horizontal asymptote. And then on the last one, I changed this to an x to the 6th. So my leading terms are 3x to the 5th in the numerator, and if I were to expand everything out in the denominator, it would be x to the 6th. That reduces to 3 over x, and if you think about what happens as x goes to infinity, 3 over x is going to go to 0. This actually tells me a little bit more. It tells me that the horizontal asymptote is 0, but it also tells me that this function looks like the reciprocal function in the long run. So in the long run, it's going to approach its horizontal asymptote of 0 from above on the right and from below on the left. So the last example we'll do today is putting this all together. So finding a rational function that meets this criteria. We have x-intercepts at 1, 0, negative 2, 0. I have put those in as factors of the numerator. Vertical asymptote at x equals 3 and x equals negative 1. I have put those as factors in the denominator. Then I'm going to put my stretch factor here. There's a horizontal asymptote at y equals 4. If there's a horizontal asymptote at y equals 4, that means the numerator and denominator degree have to be equal, which right now they are. They're both squares. Remember, we're multiplying here. So they're both x squared. That means the ratio has to be 4, so my a must be 4. I could write this function either in factored form or in standard form. And if it's in standard form, notice you can see that ratio of y equals 4 as the horizontal asymptote. But of course the factored form is better because I can see the x-intercepts and the vertical asymptotes from the factored form. We'll save holes for another day. You should be able to do almost all of your Pearson realize. Just go ahead and hold off on question number 9 for now. All of the rest of them you should be able to do.